Alright guys, welcome back. In this video we're just going to solve this circuit to find out what the voltage drop and current across each resistor is, and then we're going to come back and verify our results using Kirchhoff's voltage law. So to get started, we need to identify what the equivalent resistance is from this node to this node. We can draw on an equivalent resistor if it helps, and we can even shade in the different nodes if that also helps us to identify the difference between the nodes. So the equivalent resistance of the two parallel resistors between the green node and the blue node is 1.714 ohms. So when we think about the equivalent resistance, that's like just getting rid of this branch and basically leaving us with a series circuit. So the total resistance of the series circuit then is just R1 plus R equivalent, which is 6.714 ohms. And then we can solve for the total current, which is going to be moving like this out of the battery, and it also comes into the battery like this right here. This would be the total current moving through the circuit, again, if we imagine that these branches are gone and we're just dealing with the equivalent resistor. So it comes out of the battery, through this resistor, through the equivalent section, and back again. So the expression for that is V equals IR, and we can just rearrange that for current to find the total current as 1.34 amps. And then we can apply Ohm's law one more time to find the voltage drop across resistor 1, which is 6.7 volts. And then again the voltage drop across the equivalent resistor, basically from the green node to the blue node, which is 2.3 volts. So the voltage drop from the red node to the green node is 6.7 volts. So let's write that on, 6.7 volts. And then the voltage drop from the green node to the blue node is 2.3 volts. It's the drop across the equivalent resistor, but it's the drop from any point on the green node to any point on the blue node. So we can erase the equivalent resistor and just label on the voltage drop of both resistors as what the value that we had. So it's 2.3 volts and 2.3 volts. Now we can also indicate the polarities here. So on the battery we have the negative terminal and the positive terminal based on how the battery is drawn. And then looking at this resistor, the red node is 6.7 volts higher than the green node, so we're going to have the positive and the negative like this. Also current is flowing, positive current is flowing into the positive terminal of the resistors. And then we have the same thing down here, the positive side and the negative side, and the positive side and the negative side. I did a video on the passive sign convention of circuits, and if you're interested you can check the link in the top right corner and take a look at that as well. It talks about these polarities. But the last thing that we can solve with this circuit is we can find the currents flowing through all of the resistors. So the current flowing through resistor 1 is just equal to I total, which is 1.34 amps. And then we can solve really easily using Ohm's law again, just rearranging for current to find the current flowing through resistor 2 to be 0.766 amps and the current flowing through resistor 3 to be 0.575 amps. And you'll notice if you just add 0.766 plus 0.575, that equals 1.34. So we have 1.34 amps flowing into the green node, and then a total of 1.34 amps flowing out. And then same with the blue node, we have a total of 1.34 amps flowing in, split between the two resistors, and then 1.34 flowing out. So that is Kirchhoff's current law, saying that the current flowing in is equal to the current flowing out of nodes. And that's a nice thing to know if you check that it indicates that we've probably done everything correct. But we can also use Kirchhoff's voltage law, which states that the algebraic sum of voltages around a loop is 0. So let's erase some of the work around the outside and take a look at this one loop at a time. Let's look at the right hand loop first. Let's just draw on a direction here. Let's go clockwise. Clockwise is a nice way to go. It doesn't have to be, but I don't know, it's just nicer to look at. So when we look at this, let's start at the point on the green node, and we'll go around the full loop and we'll come back. Now when we enter an element's positive terminal, we add this voltage as a positive. When we enter an element's negative terminal, we add that as a negative, and we sum them all up to 0. And that should bring us to the correct answer. So if we do that, looking at resistor 3, we're going to have a positive 2.3 volts. And then we add negative 2.3 volts, so we subtract it for resistor 2, so we have minus 2.3, and that should be equal to 0. And yeah, definitely 2.3 minus 2.3, we have 0 equals 0, and this loop on the right is satisfied by KVL, Kirchhoff's voltage law. Let's take a look at the loop on the left. Let's draw on a direction that we're going to go. We can use clockwise again. And we can just start anywhere. Let's start right here. So when we come around, we're going to reach the battery and we're entering the negative terminal. So we'll add that as a -9. So we have -9 volts. When we come around to resistor 1, we're entering through the positive terminal, so we put that in as a positive value, so plus 6.7 volts. And when we come around the loop to resistor 2, we're entering into the positive terminal again, so we're going to treat that as a positive value of 2.3 volts. And we set that all equal to 0. Now negative 9 plus 6.7 plus 2.3 is equal to 0. So we basically get 0 is equal to 0, and this loop on the left also satisfies Kirchhoff's voltage law. So sometimes you're asked to apply Kirchhoff's voltage law, but other times if you're just solving for other things in the problem and you want to confirm that you've done it right, it's a nice check for us to use along with Kirchhoff's current law as well.